Hello, AP Chemistry. How are we doing today? Hopefully, y'all are doing well. So, today we are going to be continuing our Unit 7 notes on equilibrium. Now, for today, we're actually going to cover what is called reaction quotient. All right. You do need to make sure you've got a calculator today again. So, make sure you've got that, and we're going to go ahead and get started. Now, this is actually Unit 7.3 on the College Board. So if you do want to go in and do some of those practice quizzes that are posted there, then that is a good study resource for you. All right. So what is the reaction quotient? Well, last class we talked about this thing called the equilibrium constant, right? We talked about KEQ. Well, to solve the equilibrium constant, we use the equilibrium expression, right? Where you took those, your concentrations of your products over the concentration of the reactants, and you solved that, and that gave you your KEQ, that equilibrium constant. So what is the reaction quotient? Well, the reaction quotient is basically going to tell us, have we reached equilibrium? So what that tells me is that I might or might not have reached equilibrium at the time of the measuring. So the reaction quotient is a point in time in the chemical reaction. It doesn't necessarily mean that it's reached equilibrium. It could be at the very beginning. It could be somewhere in the middle, but it is a point in time in that reversible reaction. So when we solve for our Q, basically what we're doing is we're trying to figure out, okay, well, if this reaction continues, are we going to be making more products? Are we going to be making more reactants? Or have we already reached equilibrium, and so we will be maintaining that consistency at that point, okay? So how do I know, once I solve for Q, if I've reached equilibrium? This would be what we do. Well, first off, we do calculate this using our, essentially the same way we would calculate Kc or KEQ, right? But instead of using the concentrations at equilibrium, we're using the concentrations that they give us at a point in time, which is typically going to be the initial concentrations instead of the equilibrium concentrations. So we're typically going to be looking at those initial concentrations instead. So what I can tell is that if I've got a K equal to my Q, sorry, let's flip that. So let's say I've got a Q equal to K. What that tells me is that my system has reached equilibrium. So it's not going to favor the products or the reactants. We're going to have that consistent flow in both directions, but they're going to basically be maintaining the same rate, okay? Now, what about my Q? What if my Q is greater than my K? Well, what that tells me is that my product to reactant ratio is too large. And so that tells me that it's going to shift to the left. Now, what does shift to the left mean? Well, if you think about a chemical reaction, so A plus B in a reversible reaction produces C plus D. Looking at this reaction, if I say I'm shifting to the left, I'm shifting to the left side of my reaction, which means I'm shifting to the reactant side. So if I've got a Q greater than K, that tells me that my reaction currently has too much product. And so it's going to shift to form more reactants. So these products are then going to start to form more reactants. Okay? Now, what happens if my Q is less than my K? Well, then that would tell me that I've got too many reactants, and so it would shift to the right, to the product side. And so we would see more products being generated, more products being created, okay? All right, y'all, so now let's take a look at this problem here. So it says for the synthesis of ammonia, the value of K is 6 times 10 to the negative second at 500 degrees Celsius. In an experiment, 0.5 moles of N2, 1.0 times 10 to the negative 2 moles of H2, and 1.0 times 10 to the negative 4th moles of NH3 are mixed at 500 degrees Celsius in a 1 liter flask. In which direction will the reaction proceed to reach equilibrium? Or will the system proceed? Sorry. So the first thing that we should do is we should write out our equation. So this is a synthesis reaction. So I have N2 plus H2 in a reversible reaction produces NH3. I balance that, I get this right here. Okay, so now I've got my reversible reaction written out. So now what we do is we solve for Q. How do we solve for Q? Well, we're going to use kind of that same idea with the equilibrium expression. We're just going to call this a Q expression, but it's the same thing. So Q equals the concentration of the products over the concentration of the reactants. Okay, so concentration of products over concentration of reactants. Now, again, we're just going to plug in our formula here. So Q equals the concentration of the products, NH3, and we're going to use the coefficient of that, so 2, divided by the concentration of my reactants, N2, times the concentration of H2, that's to the third power. Now, looking at our numbers here, they say that in the experiment I've got 0.5 moles of N2. Remember, moles and molarity, or concentration, are not the same thing. Molarity is moles per liter. Well, looking here, I do have 1 liter right there. So when I do this moles per liter, it's 0.5 divided by 1. That's basically 0.5, right? So we could just plug in the moles there for our molarity. So then we would do Q equals 1.0 times 10 to the negative 4, all of that squared, divided by 0.50 times 1.0 times 10 to the negative 2 cubed. I plug that into my calculator, and what I find is that my Q equals 0.02, which, when we rewrite that, 2.0 times 10 to the negative 2. So now let's compare that to the K value that they gave us. So they told us that the K value equals 6 times 10 to the negative 2. So when we compare Q to K, what we find is that Q is less than K. So if Q is less than K, my reaction is going to shift to the right. So if it shifts to the right, that means that we're going to start to create more products. And so what we would see is that that amount of ammonia would increase. All right, so Q less than K, so reaction shifts right to form more product. And then that would be my answer. Okay? So now what I want y'all to do is to work that next problem. So pause your video, work the next problem, and then we will go over it. All right, so let's take a look at this next problem here. So what y'all first off should have recognized is that the moles that they gave us was not in molarity, right? We didn't have our actual concentrations. So the first thing that I did was I went ahead and converted those different number of moles per liter into the concentration that we use, which is moles per liter, right? So 1 mole per liter for the HF, 0.1 moles per liter for the H2, and 0.15 moles per liter for the F2. Then I did my Q expression here. So Q equals H2, concentration of H2, times concentration of F2 divided by the concentration of HF squared. Plugged in my numbers, and I found that my Q equals 0.015, which was 1.5 times 10 to the negative 2. And I compared that to what I had for my KEQ, which was 1.0 times 10 to the negative 2. So it is greater than my K. So since Q is greater than K, the concentration of the products is going to decrease. Okay? All right, so let's take a look at this. So this is just another way that you could see this written out, another way to ask this question. So consider the reaction CH3CO2H aqueous plus C2H5OH aqueous in a reversible reaction produces CH3CO2 C2H5 aqueous plus H2O, which is a gas. And then they do tell us that our KEQ is 2.12. So for the following mixtures, A through D, will the concentration of H2O increase, decrease, or remain the same as equilibrium is established? So all we're doing here is we're solving for Q, and we're going to be comparing it, okay? Once we've got our Q, then we have to decide, is it product or reactant favored? And so which direction will we shift? And then once we've got that, we can decide on, will my H2O increase, decrease, or remain the same? So first things first is to solve for Q. So Q equals the concentration of CH3, CO2, C2H5 times the concentration of H2O divided by the concentration of CH3, CO2H times the concentration of C2H5OH. I plug in my numbers for that, and I find that my Q equals 0.22 times 0.10 divided by 0.010 times 0.010. And what I find is that my Q equals 220. So when I compare that to my K, which was 2.2, Q is greater than K. And if Q is greater than K, what does that tell me? Q greater than K tells me that the product to reactant ratio is too large, so the reaction will shift to the left, forming more products. So then my H2O will decrease. Okay? So then this would be my answer. All right, now I want y'all to solve this next problem, and then we'll go over it. So pause your video, solve the problem, we'll go over it. Okay, so here's what you should have done. So we found that Q equals 0.22 times 0.0020 divided by 0.020 times 0.10, and I found that my Q equals 0.22. Okay, that tells me that Q is less than K, which if Q is less than K, then the product to reactant ratio is too small, so the reaction will shift to the right, forming more products, and so my H2O will increase. Okay? All right, now I'm going to leave these next two problems for you to do as practice. You can find that key online, and you will be able to check your work there. All right, and we're going to go ahead, and I'm going to do one more problem with y'all, see one more way that you could see this data, and in this case, it's just in a table, and then I will leave y'all to do whatever you need to do to prepare for this section of the unit. So, from the above data, calculate the reaction quotient and predict in which direction the reaction will proceed. So some of the things that they tell me is that the value of Kc for this reaction is 5.10. And then they do tell me that it is a non-equilibrium concentration. Basically, all that's going to be telling you is that you're solving for Q, not K. Okay? All right, so I am solving for Q here. So Q equals products over reactants, so concentration of H2 times the concentration of CO2 divided by concentration of CO times concentration of H2O. So then my Q equals, so H2 was 0.42 times CO2, which was 0.37, divided by CO, which was 0.15, times H2O, which was 0.25. I plug that in, and I find that my Q equals 4.14. Okay, so my K, if you remember from up above, they told me that it was 5.10. So Q is less than K, so that tells me that the reaction would proceed to form more products. Again, we're trying to reach that equilibrium. So then Q is this. So that would be my reaction quotient. And then my other answer for the direction, it would proceed to form more products, which means it is proceeding to the right. Okay. So I want y'all to do that last one as practice, and then I'll slide on down so y'all can see what the answer is. And then we will move along. Okay. So pause your video, solve the problem, and let's get started on it. All right, so here's what you should have ended up with. So you should have found that Q equals 8.92 times 10 to the negative 3. So we found that Q was greater than KEQ. So that tells me that the reaction would proceed to form more reactants. Okay, and that is it for the reaction quotient set of equilibrium. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.